It's good. Okay, so hi, my name's Harun, and I'm a postdoc at the Biomedical Informatics Group at ETH Zurich. And I'll be talking about some of the work that we've been doing lately on sequence to graph alignment. So recently, there have been some large-scale efforts for indexing collections of raw sequencing data from large databases such as the SRA. And these include our recent Metagraph effort, which we put out along with tools such as Pebble Scout and KM Index. So these are the kinds of data sets that we would like to target in the future for targets for search. So these tools work in a very similar way to index sequencing sets. So I'll illustrate it here with a small example. So suppose we have these 4 samples, and then we digest them into k-mers, and then after doing some lightweight assembly, graph construction, and graph annotation, we end up with what you see here as an annotated de Bruijn graph, where the graph nodes represent the k-mers that are observed in your input samples, and the edges are implicit. And the annotation is used for representing metadata on top of this graph. So these can include labels or those otherwise known as colors, or you can represent k-mer counts, or if you want to have a lossless representation of the sequences that are input, you can represent coordinates on top of this graph as well. So now a primary question, given this type of index, is how can I align sequence queries against an index of this structure? And a simple way to do this kind of query is through a process called pseudo-alignment or exact k-mer matching. So I'll illustrate it now with an example. So given this sequence, we start by first breaking it down into seeds and then mapping these seeds against the graph to get anchors, where an anchor is a matching between a seed and a graph node. And here you see that we have different anchors for each, where's my cursor? Okay, we have different anchors for each color in the graph. And then from here, given these anchors, you can then traverse the graph and keep track of edits in order to produce full alignments. So now, what does a sequence to graph alignment consist of? The first part is a graph walk and the spelling of this walk, which we refer to as the target sequence. Next, we have a per character alignment between the query and the target sequence, represented here by both the matching between the 2 sequences, a cigar string, and the computed edit distance. And finally, we have a set of labels associated with the nodes in the graph walk. So now here I've covered in a bit of detail the seeding portion of the seed chain extend paradigm that's typically used in sequence to graph alignment. So now I'm going to cover in a bit more detail the chaining and the extension portion of this heuristic paradigm. So the chaining problem is basically the problem of finding a high-scoring sequence of anchors that is in order in both the query and in the graph. And by in order in the graph, I mean there exists a walk from one anchor. Where's my cursor? Yeah. So there exists a walk from one anchor to the next anchor within the graph. And then once we have these chains, we then extend them into alignments in 2 steps. The first step is by connecting anchors together with global alignment. And the second step is by extending from the first and the last anchor in the chain using ends-free extension. So from here, the chain acts as a skeleton, and from which you do the full alignment. So now, when we do extension or global alignment, the approach that you use to traverse the graph depends on the properties of the input data that was used to build this graph. And there are different levels of restriction that you can impose on this traversal. The most restricted is one that we refer to as trace-consistent alignment, where the walk in the graph has to be a substring of one of the input sequences, is most analogous to blasting against a collection of reference genomes. And this is applicable if you have a coordinate system defined on top of the graph. On the opposite end, we have what we refer to as label-free extension, where all walks in the graph are considered to be valid. And this works for single species pangenomes, where you can assume that a number of different walks in this graph are biologically relevant recombinations. An intermediate mode is label-consistent alignment, where all nodes within the walk have to share a common label. And this works well if you're indexing a collection of contiguous assemblies where you know that these long paths exist to be able to align your query against. But for a number of samples in the SRA, these contiguous assemblies don't exist because they were sequenced at low sequencing depth. So for these fragmented assemblies, we introduced this approach called multi-label alignment, which allows you to change labels and to combine sequence information from different samples to overcome this fragmentation. So now I'm going to go over how we do multi-label alignment, because this is a more challenging problem than some of the previous alignment approaches that I mentioned. So starting with our anchor set, the first thing we do is a single label anchor chaining, meaning that we produce chains of anchors, or one label at a time. And then from there, we extend these into alignments that target a single label at a time. And we refer to this process as SCA. Afterwards, we extract anchors from these single label alignments, producing a subset of the original anchor set. So then given this smaller subset, we can then do a multi-label chaining, allowing us to take advantage of some new alignment operations that we introduce, to be able to combine fragments from different alignments to different labels. And we refer to this as LC plus NC, and in the next slide, you'll see where these acronyms come from. Finally, yeah, okay, here it didn't turn out so nicely, but what ends up happening afterwards is that we combine together fragments from the single label alignments using the multi-label chain as a skeleton to produce multi-label alignments. So now the two operations that we introduce are referred to as label change, where we can change from, let's say, one species to another, and the other is node length change, where we can reduce the length of K dynamically within the graph. So as an example of the first operation, suppose that you're traversing along a portion of the graph that has a blue label, and then you need to pick between transitioning to the yellow and the red. So to decide this, we look at the Kamer set for the blue label, and then we compare it to the Kamer sets for yellow and red. And what we see here is that there's a very big overlap between the blue and the yellow, and in this case, no overlap between blue and red. So we assign a low score, or if these two labels share very few Kamers. So in this case, our traversal would prefer to go from blue to yellow. To illustrate node length change, let's look at this small example of a fragmented graph where this lower blue fragment is separated from the rest of the graph. Now, if we had constructed this graph using a smaller value of K, then there would exist a path within the graph to go from one node at the bottom left all the way to the top right. But we introduce a penalty so that this happens to a more limited extent. And we also introduce a restriction where you can only change in your node length if you're already at a node that is of maximum length K, or the defined maximum length K. And this is to help reduce the search space. So now with these two operations, we can overcome fragmentation in the assemblies that we index using our graphs. So now we've introduced all of these changes and this new procedure for alignment. Now let's see how well this actually performs. So to do this, we simulate a fungi kingdom pangenome from GenBank chromosomes. So given a collection of chromosomes, we simulate reads from different platforms. So we have one collection of Illumina reads, which we use to create our simulated pangenome graph. And then we have other query sets from a variety of platforms that we then query against this graph. So the first step is constructing the graph. And then the second step is aligning these query reads against this graph. And then from here, we then use the labels that we fetch from the graph during this alignment to create a taxonomic profile for each read. And then when we want to evaluate how our alignments perform, we have these three criteria that we look at. The first is whether our alignments are actually longer. The second criterion is whether our alignment scores are higher, meaning we're getting a better quality alignment. And the third one is whether the labels that we are combining using these new operations are biologically relevant. And we can do this because we know what the ground truth labels are for each of our reads. So we can compare these to the taxonomic profile that we get from the alignment. So now here I'll show you some violin plots of how much of the query reads were covered by the longest alignment when we do multi-label alignment and when we compare to other tools. So the two main tools we compared against were Graph Aligner and Plast. And we see that with our simulated pangenome, we're only managing to align a small fraction of these reads. And using our single label aligner as a baseline, we see that we don't get too much of an improvement here. And then if we introduce our label change operation, we get a slight improvement. But combining this with our node length change operation to add extra contiguity to the graph, we are able to align much more of our query sequences as compared to before. So now looking at actually how accurate our alignments are and not just how long they are, we consider two criteria. The first one is looking into setting different score cutoffs where we say, okay, if the score is above a certain level, we say that the read is alignable, and then we compute a recall from this. And then afterwards, we can then plot the taxonomic precision versus recall curve and then measure the area under that to get a single measure of accuracy. So looking at Graph Aligner and Plast, we see that our recall is generally low. We need to set a low cutoff to get 50% recall. And we see similar features when we have our baseline SCA and SCA with our label change scoring, though we do note we get an improvement in the area under the precision recall curve. But then if we introduce, label change scoring and also our node length change operation, we see both an improvement in our scores measured here by an increase in recall, and we also see an improvement in the area under the precision recall curve, meaning that we are combining together fragments of biologically related samples using our operations. So in summary, we want to target the problem of aligning to fragmented assemblies, because these assemblies if you use traditional alignment approaches, just lack long contiguous paths, which produce short alignments. And we want to take advantage of the fact that pangenome graphs index multiple samples and we can share information between these samples. And with multi-label alignment, we are able to produce longer alignments by incorporating fragments and overcoming gaps in the graph. And with our novel operations, we ensure that we do this in an accurate fashion. And you can check out our paper for some more details on our scoring model, how we do chaining, and exactly how we measure profile precision. And in the future, we want to look into improvements to our indexing and also ways of comparing ourselves to other aligners that are based on variation graphs, which we were not able to find a fair way of doing at the moment, but we are willing to discuss this with other people. And before I finish, I want to bring up a fact that with this conference being in Canada and with previous conferences in Canada having issues with several people not being able to get visas, and this essentially acting as a double punishment because said people have to undergo many hardships trying to build careers abroad. I think myself and other Canadian citizens in the audience should really bring this up with our members of parliament so we can let them know that this is a real issue that we need to overcome. So now I would like to open the floor for questions, and thank you for listening.
Questions?
I was wondering if you were able to compare by looking at running it GATK or deep variant and looking at the variants called using the alignments.
I mean, I guess if you were to do like a variant aware aligner, like what we would do is we would just combine together their, let's say, alignments to different samples. So I'm not sure. Let's say, how doing GATK would kind of improve things. Or maybe what we could do is we could let's say take existing aligners by GATK and then applying our method to see if that gets us an improved accuracy compared to those. We thought about this, but we haven't had time to really implement it yet. But yeah, that's a very good suggestion.
Yeah, I guess the biggest hurdle that you would have to overcome is your alignments you'd have to do some ground like software engineering to get a SAM file that could be then plugged into GATK or deep variant. Which can be challenging or time consuming from a software engineering perspective.
Yeah, that's true. But yeah, theoretically possible.
Right.
Yeah.
Right. Any other questions? Okay, so maybe I can ask one. I think you mentioned Chirag Jain's study there with mini chain, and so I was wondering a bit about the sort of, did you compare against the mini chain? I think they penalized like haplotypes in the chaining approach, and to me it seems similar. So what's your take on this?
Yeah, so I guess two things to mention. One, we couldn't do a direct comparison because their aligner assumes that you have a variation graph and not an overlap graph. So I couldn't find a nice way of, let's say, converting our De Bruijn graphs to variation graphs so we could directly run. But what we did do, and what's present in the supplement of our paper, is that we implemented their haplotype change scoring method within our multi-sequence or multi-label alignment approach, and we found that we actually got lower accuracy compared to the one we did. But they're working in a different context where they're working with human pangenomes, where you can kind of assume that switching between different haplotypes is more or less going to have similar scores. So a constant haplotype switching score works well. But if you have a very diverse pangenome like ours, you can't really make that assumption anymore.